August public tour. Tonight we're going to hear a talk from a PhD student named Jamil Shariff. And he's actually going to be a doctor soon. He's defending his PhD within a week or so. So for his PhD, Jamil has worked on building and designing telescopes that are flown on high altitude balloons from Antarctica. And questions that he works to answer are questions like, how did the stars form in our galaxy? And what happened at the very beginning of the universe? So Jamil actually was part of the public tour a few years ago. He helped run and maintain the tour in 2011 to 2010. So we're very happy to have him talk today in what will be his last talk of his PhD. So please skip around to Jamil.
Okay, can everyone hear me in the back? Oh, it sounds like it. The mic's working well. So thank you, Lisa, for the very kind introduction. Today I'm here to tell you a story. And it's the story of how I came to be on a team of scientists who traveled to Antarctica to build a telescope that we launched on a giant stadium-sized balloon nearly into space in order to learn more about what happened at the very beginning of the universe. And our story begins in fall of 2008. One second. So back then, as a younger and much more idealistic man, I was just joining the graduate program in the Department of Astronomy, and I was trying to decide what I wanted to do my research on. And I heard about this oddball research group run by this oddball professor that designs and builds balloon-borne telescopes. And the idea of this kind of project really appealed to me because I'm the kind of person who wants to be developing the new technologies that enable new scientific discoveries. So that professor, whose name is Bart Netterfield and who's now my PhD supervisor, gave me a tour of his lab, and at the end of it he gave me a rundown of which projects would be available for me to sign on with. And it basically came down to a choice between these two experiments, Blast Pole and Spider. So the goal of Blast Pole was to take images of clouds of interstellar gas and dust in our galaxy, places where stars are either forming today or are going to form in the future. And Blast Pole was actually an upgrade of a previous telescope called Blast that had already flown on a balloon. So most of the technology involved was proven. And as Bart explained to me, the project was likely to produce a fair number of scientific papers, each one describing a relatively small but hopefully interesting discovery. In contrast, Spider's goal was to measure one specific thing. We wanted to measure the value of one number that goes into our theories of the early universe. So the expected number of papers to come out of this project was approximately 1. And it was going to be either a paper describing a groundbreaking discovery of fundamental importance to our understanding of the Big Bang, or it was going to be a paper describing the lack of said discovery. So talk about putting all your eggs in one basket. Not only that, but most of the technology that was to fly on Spider was brand new and totally unproven. So presented with this information, it seemed to me that Blast Pole was clearly the safe bet in terms of career choices. So of course, I chose Spider. These questions are both very important. Ultimately to me, this one just seemed more compelling. And that brings me to what we're trying to find out with Spider in the first place. As many of you know, Our prevailing view of the universe and how it works is based on this standard Big Bang scenario, which is this idea that the universe was hotter and denser at earlier times, and it has subsequently expanded and cooled, and it is continuing to expand. So we have a fair amount of pretty strong observational evidence that this is true. But one of the most important pieces of evidence is perhaps the existence of something called the cosmic microwave background, or the CMB. And what that is it's a glow that we see when we look out into the distant reaches of the universe, coming at us from all directions. And this glow is the primordial light left over from the heat of the Big Bang. So I have a video that tries to explain that. And in this video, we start off at Earth, and we zoom out to farther and farther distances. So eventually, we pass Saturn, we leave the edge of our solar system, we pass through our local stellar neighborhood, through some nebulas and star-forming regions, and we emerge out of our spiral arm of the Milky Way galaxy. And as we move farther and farther out into the universe, we see it as it is at earlier and earlier times, to the point that eventually we reach back to a time when the very first stars and galaxies were forming. And before that, as we go farther back, we reach back to a time when there were no objects at all. The universe was so hot that all of the matter in the universe was in the form of this smooth and almost featureless gas. And that gas was at a temperature of thousands of degrees and was glowing white hot, kind of like the surface of the sun. So a prediction of the Big Bang model is that if I look out far enough in distance, I should be able to look all the way back to a time when the universe was filled with this hot, glowing, primordial gas. So of course, immediately a problem presents itself, which is that I don't know about you, but I've never seen that. And the reason for that is as follows. Initially, that gas was at a very high temperature, but as the universe expanded and cooled in the ensuing billions of years, the glow from that gas got dimmer and dimmer, and its color or wavelength shifted until it was in the form of a type of light that we can't even see with our eyes. It was in the form of microwaves. So even though when we look up at the sky, we don't see this glow with our eyes, if we could put on our microwave goggles, and suddenly we would see the CMB, this glow coming at us from all directions. And that's what this map of the entire sky, showing how much microwave light there is across the sky, shows us. This is like a false color image, where the color represents brightness. So as you can see, aside from this bright band going down the middle, which is our galaxy, the color is the same everywhere. It's as though the glow of the CMB is remarkably uniform across the whole sky. Or so we thought, until we began to observe it with more and more sensitive telescopes. And when we did that, we eventually learned that there are, in fact, fluctuations in brightness from one spot to another on the sky. And they correspond to fluctuations in the temperature of that hot, glowing primordial gas that you saw in the video. And those fluctuations in turn are because, as you saw in the video, that gas was not perfectly smooth, not perfectly featureless. It was kind of clumpy. There were places where there was slightly more gas than average, and there were places where there was slightly less gas than average. So this is our baby picture of the universe. This is our snapshot of what it was like almost at the very beginning. And because we have that snapshot, we're able to learn a great deal about the universe. For example, the CMB allows us to measure some of its basic properties with remarkable precision. Things like its age and its composition. Not only that, but it enables us to determine how those clumps grew over time because of gravity to eventually form structures and objects like galaxies. So this all sounds really great so far. But of course, there's a problem. And the problem is simple. Where did all those fluctuations come from in the first place? Why are they there? And a related problem is, why do they have the strength that they do? you could imagine that if those fluctuations in the primordial gas were stronger or weaker at the beginning, the universe would have turned out very different today from what we observe. For example, if the fluctuations were weaker, then this clumping together of the gas would have taken longer because it would have been slower. And maybe there would not have been enough time for galaxies to have formed by the present day. So the strength of these fluctuations is like a little knob that you turn in your theoretical model. And if you don't set it just right, we don't exist. But the Big Bang model offers absolutely no explanation as to why the knob is set the way it is. So a solution that was proposed to this problem is a theory called inflation. And inflation says that in the very first instance after the Big Bang, the universe underwent a period of dramatic, rapid, accelerating expansion, to the point that small features on the subatomic scale that quantum physics says should be there, small subatomic scale fluctuations, were blown up in size to like a cosmic scale. And so this provides a natural explanation for where those initial fluctuations came from. Now you're probably looking at this and saying, this sounds pretty contrived, right? This is like a thing you just added on to the theory. And it makes everything work out, but we'd really like to know whether it's true or not. Fortunately, like any good theory, inflation makes some predictions that we can go out and test observationally. And one of those predictions is that that dramatic expansion event at the very beginning of the universe would have produced these sort of ripples in the fabric of space and time that we call gravitational waves. And furthermore, if these gravitational waves are there, we should be able to detect them by an imprint or a signature that they leave in the CMB light. More specifically, an imprint that they leave in the polarization of the CMB light. Okay, so the next obvious question is, what is the polarization of light? You may have heard that light is like a wave, and you can think of light waves coming away from a source of light in the same way that you think of these waves, these ripples on the surface of a pond expanding outward from the source of a disturbance. So the question is just, which way are the ripples going? Which way are the ripples going? Are they going up and down like this? Or are they going from side to side like this? So this light wave is coming at you and it has a direction. And we call that direction the polarization of the light. And they make use of this in the 3D movies, right? So where one eye sees one polarization and the other eye sees the other polarization. And that's what allows you to simultaneously watch two different movies that are filmed from two slightly different angles. All right. So if the light has a direction, then what we can do is we can point our microwave telescope at a spot on the sky and measure not just how bright the light coming from that spot is, but also what direction is the polarization of the light coming from that spot. And we can represent that direction just by drawing a little straight line on our map and saying at this spot on the sky, the polarization of the light is oriented the way this line says it is, right, in that direction. And in this other spot on the sky, it's oriented like this. And you're going to end up with some kind of random pattern of polarization directions across the whole sky, just like the pattern of the brightness fluctuations is random. But it turns out that what you can do is you can construct or compose any random pattern of polarization directions by mixing together these two non-random patterns that you see here. And on the right we have kind of a swirly pattern, and on the left we have a pattern that is not swirly. And our overall random pattern of polarization directions is some mixture of the two. Now the kicker, the important piece of information here, is that the swirly pattern will only appear in the polarization of the CMB if gravitational waves from inflation are present. So what we can do is we can measure the polarization directions of the CMB, figure out how much swirliness is in our mixture, and that will tell us not only that inflation happened, but also what the strength of those gravitational waves produced by inflation was, and therefore how much energy was involved in inflation. Okay. Unfortunately, that's not as simple as it sounds. So in this computer simulation, you can see a patch of sky like what might be observed by a spider, and you can see the pattern of the CMB polarization directions. And one of the simulations was made for the case where there was no inflation and there is no swirliness in the pattern. And the other simulation was made for the case where there is swirliness in the pattern. What I'm going to do is I'm going to flip back and forth between them, okay? So you ready? Watch carefully. All right, that's without swirliness, with swirliness. All right? So the difference is barely discernible. And this is for a fairly optimistic computer simulation, right? So the point is, no experiment so far has succeeded in measuring this effect from inflation. This is what SPIDER is trying to do. So I realized that was a lot to take in all at once, so I'm going to try and summarize. The basic progression is this idea that if inflation occurred at the beginning of the universe, it would have produced these ripples in space-time called gravitational waves. And the gravitational waves in turn should leave their imprint in the polarization of the cosmic microwave background. Something that hopefully we can measure. And when I was learning about this, I thought this was pretty profound. Not only that we can come up with answers to some of these fundamental questions, but also that those answers are testable, that there's a physical machine that we can build to do a measurement of the oldest light in the universe in order to try and test our theories of what happened during its very first moments. And so, getting back to the story, I set to work, helping to build that machine. SPIDER is a telescope that has the ability to measure really, really faint or weak signals like this one in the CMB polarization that we're trying to detect. And there are two reasons for that. One is that it flies on a balloon lifted above most of Earth's atmosphere. And the second reason is that it has state-of-the-art microwave cameras behind each telescope that are very, very sensitive. And I'm going to come back to this first reason later. So it's a collaborative effort. There were maybe 5 different universities involved in actually building it. And this is a picture of our team down on the ice. And this is SPIDER. So it consists of these 6 microwave telescopes here. And in order to work properly, those telescopes have to be cooled down to very, very low temperatures. So they're all embedded inside this gigantic tank full of liquid helium. And then that thing is massive. It weighs more than 3,000 pounds. So it has to be supported by a lightweight but strong structure down here that we call the gondola. And it's the gondola where all the onboard systems, such as computers, electronics, sensors, and mechanical systems that allow us to control the experiment in flight, live. And it's actually that aspect of the experiment that we worked on here at the University of Toronto. Basically, everything that enables the experiment to fly on a balloon. And let me tell you, that was no easy feat of engineering. A balloon places so many constraints on what we can do. Things can't be too heavy. And all of your systems have to absolutely work before you launch the experiment, because once it's in the stratosphere, you can't exactly go up and fix it when it's not working. Not only that, but it's very difficult sometimes to send commands to the experiment, to SPIDER, to tell it what to do. So we can do that by satellite, but that's not always available. And even when it is, it doesn't always get there in a timely fashion. So basically, we had to design the experiment so that all of the systems could be more or less fully automated. SPIDER's just up there doing its thing without any intervention from us on the ground. And a related problem is this telescope is dangling from a string, right? Okay, so it's actually a steel cable, but it's still very difficult to control how the telescopes are pointed or oriented. And that's important because if you want to take images of the sky, you need to be able to make sure that you're looking in the right place at the right time. And that was actually an aspect of the experiment that was my major responsibility. Now, because of this situation where SPIDER's totally automated, and when it gets up there, it actually kind of scans back and forth and up and down across the sky like this over and over again, all by itself, making a map of the sky. So because of that, my PhD supervisor sometimes likes to call SPIDER a killer robot in space. But actually, here's what the killer robot really does. So you can see we're testing it. Let me turn that down a bit. it's actually hanging from the ceiling from a crane. So it's not touching the ground, nobody's pushing on it. It's rotating entirely under its own power and under its own control. And it's actually moving pretty unnervingly fast, considering how large an object it is. We're talking about a 2-ton telescope that's almost 20 feet tall. So I'm proud to be able to say that I was able to make that work. But in order to do so, I had to engineer a system that made use of all of these things. Not only that, but this video was taken in 2013, and remember that our story started in 2008. So it took a lot of years to get to this point. So at this point, you may be wondering, if this is so complicated and difficult, if putting it on a balloon requires you to do all these extra things and has all these complications, why are you doing it? Why are you going to put your telescope on a balloon? Why don't you just leave it on the ground where things can be as big and heavy as you want, and when something breaks, you can just walk over and fix it? And in the end, it comes down to Earth's atmosphere. Earth's atmosphere hinders our ability to observe the cosmic microwave background, and it does that in 2 ways. The first way is that it partially blocks out some of the microwave light coming from space. That's being represented here. And the second way is that the atmosphere itself emits some microwave light. It glows a little bit. And that light is going to be detected by a telescope on the ground. It's going to kind of wash out the CMB signal that you're trying to detect a little bit. So by taking our telescope and lifting it above most of Earth's atmosphere, we no longer have to contend with these problems. And the kind of balloons we're talking about are not exactly small. Here's a picture of what one looks like just after being launched. And when it gets up to its final altitude, it expands to this size here. This is the Washington Monument for comparison. So it expands to be more than 100 meters in diameter. It goes up 4 times higher than a passenger jet, and it can lift up to 8,000 pounds. So that's why we do this from a balloon. The next question is, why Antarctica? Why do you launch your balloon from Antarctica? And there's basically 3 reasons for that. The first is that in Antarctica, in the summertime, the winds are what we call circumpolar, right? So they swirl around the South Pole in a kind of polar vortex. So what you can do is you can launch your telescope from here, have it circle around the continent in 2 or 3 weeks, and then hopefully bring it down in a place that's convenient for recovering the experiment. And the second reason is that there's continuous daylight in the summertime in Antarctica. The sun is up all the time. So that provides you with a continuous source of solar power. And it also means that because you're not switching between day and night, the temperature isn't changing, and so the altitude of the balloon isn't changing. It's stable, and it can stay up for a longer period of time. And the third reason is that you're flying over completely unpopulated areas. So all of these things enable what we call in NASA speak long duration ballooning, or LDB. And the way it works is that some team of scientists from various universities come together and decide they want to build some experiment. And that experiment becomes the payload, the thing that's carried by the balloon. And then the NASA balloon program itself provides the balloon and the launch vehicle and the support personnel. And that's based out of Texas. So in the year that you want to deploy your experiment, you have to do all of these things in this order. First, once you think it's working reasonably well, you disassemble it and you ship it down to the NASA balloon facility in Texas. They call that CSBF, the Columbia Scientific Balloon Facility. And the idea is that you put it back together, you test our equipment with NASA's equipment, and make sure everything works together. And that can take up to the whole summer. And you have an end of August deadline to then again disassemble the experiment, put it into a bunch of sea containers, and ship it on a boat to Antarctica via New Zealand. So that has to happen by the end of August. And then by late October, early November, we ourselves, the members of the science team, have to head down to Antarctica with the goal of hopefully assembling the experiment and having it ready for launch by mid to late December. So at this point in our story, things were going pretty well. They were coming together. And what we had to do was decide when we wanted to initiate this whole process. When were we going to deploy Spider, first to Texas and then to the ice? Well, we wanted to try and go for it in 2012, but we had some problems with those state-of-the-art microwave cameras I told you about. As is often the case with any new technology, it doesn't always work right away, and you have to go back to the drawing board and redesign certain things. So this is a picture of one of those cameras, and it lives here at the back end of each of the 6 telescopes. There is one of these cameras. So it wasn't quite working, so we needed at least another year to get that problem sorted out. But then once we had that problem sorted out, we said, this is it, we're doing it. Texas, here we come, right? Specifically middle of nowhere, rural East Texas, in a town called Palestine, but actually it's pronounced Palestine, take note, Palestine, Texas. And you know, it's really not such a bad place to spend 3 months of your life once you get over the extreme heat and the bugs and the bad food. I actually preferred being in Antarctica, to be honest. But no, Texas was pretty cool. Some interesting stuff happened. I got a new haircut. We befriended a dog, an abandoned dog who was hanging around the balloon base, and named her Laika. Bonus points if you get the reference. And we spent many a warm summer night doing tests on Spider. So this is a picture looking into the testing facility from outside. So we spent 3 long, difficult months working on this experiment. It was our very first shakedown of the experiment, so a lot of things didn't work properly. Most notably that giant helium tank I told you about before. That thing was very difficult and wasn't quite working right by the end of this process. But the end of August was nearing, and we said, this is the best we can do. We have it in a fairly reasonable working state. Let's ship it. Let's put it on the boat. Let's ship it down to New Zealand. So we did that. It got there. September rolled around. October rolled around. We were getting ready to go there ourselves. And then this happened. So, as some of you may recall, in October 2013, the US federal government decided that for 2 weeks they didn't want to do their job. So they shut down, and this was problematic because all 3 research bases in Antarctica that the US operates are run by the National Science Foundation, which is a federal agency whose funding had just been put on hold. Okay. So a 3-week delay doesn't necessarily sound like the end of the world, right? Or a 2-week delay. But in ballooning, timing is everything. And by the time they resumed operations, and they would have been ready for us to go down to Antarctica, we would not have had enough time to assemble Spider and get it ready for launch by mid to late December. So the whole process was postponed by a year. So this was actually really devastating news. It was bad for the project, it was bad for people's careers, and I actually started to wonder if I would ever see Spider fly. It had already been 5 years since this process had started. And I started to wonder if I would ever be able to go to Antarctica. But we didn't give up. We had them ship Spider all the way back from New Zealand on a boat back to the United States, put it back together at Princeton University, fix some of the problems with the helium tank that wasn't working, and just increased our overall level of readiness. So that by the time August 2014 rolled around, we were ready. And that brings me to the next part of my story. So, one of the most common questions I get about Antarctica is how cold did it get when you were there? And the answer is it sort of depends where you are and when. The South Pole is a really inhospitable place, especially in the winter. It's the coldest place on Earth, essentially. But the place where I lived, Mcmurdo Station, is a little bit better. In fact, my stay was from late October until mid-January. So during that time, the temperature sort of started off hovering around minus 20 degrees Celsius, and then climbed steadily throughout the season until it was basically approaching 0 by January. And of course, as I mentioned before, it was summertime, so we were living in perpetual daylight, which took a little bit of getting used to. So where were we going? The bottom of the world. But where specifically? This place here, Mcmurdo Station. And if we zoom in a little bit on that, we can see that it's kind of on this patch of ice here. There's some permanent, somewhat permanent, glacial ice called the Ross Ice Shelf. And if you look down in the bottom right corner here, you see that there's this tiny little island. You zoom in on that and it looks like this. That's Ross Island. And then if you zoom in a little more on this peninsula here, you see that just at the tip of it is McMurdo Station, where we lived. And just around the corner from it is Scott Base, which is operated by New Zealand. So this is the US base, this is the New Zealand base. And this stuff here is sea ice, so it comes and goes with the seasons. It becomes open water sometimes. And this stuff here is the glacial ice, the ice shelf, which is much thicker and stays around. And the place where we launched our balloons from was somewhere out here, 10 or more kilometers away from McMurdo Station. So how do you even get to Antarctica in the first place? Well, the first step is that you have to get to New Zealand. So in order to do that, I just took commercial flights, Toronto to Dallas, Dallas to Sydney, Sydney to Christchurch, New Zealand. And once you're in Christchurch, you have to take a US Air Force cargo plane. In this case, it was a C-17 to McMurdo Station. And on the way back, it was similar, except it was a little bit more arduous because, first of all, I was taking a slower plane from McMurdo Station to Christchurch. I was taking a C-130. So instead of taking 6 hours to make this traverse, it was 9 hours. And then I had an overnight in Christchurch, and then I had to go from Christchurch to Auckland, Auckland to Tahiti, Tahiti to Los Angeles, Los Angeles to Chicago, and Chicago to Toronto, for a total of some 32 hours worth of traveling. So this is what the US Air Force C-130 that I flew back on looked like. And you can see that it's specially equipped with these skis here. So the first thing you do when you get to Christchurch is you go to the so-called CDC, the Clothing Distribution Center, and they give you all kinds of gear. They give you a Canada Goose down parka, they give you snow pants, they give you a toque, they give you a balaclava, they give you glove liners, they give you gloves, they give you boots. They give you 3 different kinds of thermal underwear, they give you a fleece jacket, and so on and so forth. And they call this ECW gear, or extreme cold weather gear. And even though conditions at McMurdo Station in the summer are actually pretty mild for all of this, you have to carry this gear around with you everywhere you go. Because the weather in Antarctica is very unpredictable, it can change, the visibility can become bad, the winds can pick up. So they require you to carry a big orange bag with all this stuff in it everywhere that you go. Now remember that the C-17 was a US Air Force cargo plane, not a passenger plane. So we were actually in these fold-down jump seats lining the bare walls of the fuselage, and in the middle of the plane was cargo. And my friend Ziggy was lucky because on his plane, one of the pieces of cargo was actually a helicopter. So I was jealous of that. I took this picture shortly after arriving of the C-17 that I just disembarked from. And here's me standing at McMurdo Station. So it's pretty difficult to describe what a thrill it was to be standing there after 6 years of working towards this moment. McMurdo Station looks a little bit like this, and it actually has all of these amenities. You can read them, so it's almost like a small town. Our accommodation was sort of dormitory style, so we lived in these brown buildings here. So we weren't exactly roughing it. I mean, there are scientists who go out to remote field camps living in tents, like geologists and biologists, but that's only for short periods of time. It would not be feasible to live under those conditions for 3 months. This is one of the biggest research stations in Antarctica, and at the peak of the season, it has almost 1,000 people living there. Our daily routine: we would take a transport called Ivan the Terrabus, and it would carry us down and around the peninsula, past Scott Base, and out to our work site. And that work site, let me tell you, had some spectacular views. If I walked out of the building where we were assembling Spider and looked north, I saw this, which was Mount Erebus, looming over our work site. This is the world's southernmost active volcano. So there was an active volcano looming over our work site. And that's just if you look north. If you look west, more spectacular mountain ranges, and you can see Williams Airfield in the foreground where the C-130s land. And we saw some wildlife down there. Skuas are these big, brown, ugly, aggressive seagull-type birds. And if you make the mistake of carrying a plate of food from the cafeteria to your dorm, they will dive bomb you for it. You gotta watch out. And we saw Weddell seals. And they like to hang out on the ice sheet outside Scott Bay. So here's a seal pup and its mother. And here are some close-up shots I got of them as we were walking around on that ice sheet. And when I say we saw seals, I mean that we saw a lot of seals. As the season progressed, their numbers seemed to just increase, and all they would do all day is lie there on the ice sheet writhing around. That's their life. Okay. So that was some of the wildlife we saw. Anything else? You guys can't fool me. I know the only reason you came to see this talk, the only question I got when I told people I was going to Antarctica is, are you going to see a penguin? So I hate to disappoint you, so I won't. I actually saw a grand total of 3 penguins during my stay there. And that was one lone penguin on each of 3 different occasions. So the first one was this emperor penguin. It came by our workplace, but it kept its distance. Here's another picture I took of the emperor. These penguins can get pretty tall, like almost a meter tall. And this is what he was doing when he came by. That's definitely the best part. And the second species of penguin that we saw was called an Adelie penguin. They were much smaller. They were maybe this big. And while the emperor penguin kept its distance, the Adelie penguin really did not. This is maybe one of my favorite pictures from Antarctica because it's a day when we have Spider out on the porch for testing and people are doing work, and then all of a sudden there's just this penguin tottering around in front of the building. But you know what, enough of that. We're here to do serious science stuff, right? That's why we came down here. That's why we came to the long duration balloon facility out in the middle of the ice shelf, which has these buildings called high bays, which are kind of like these big hangars where we assemble the payloads before we launch them. So don't worry, things got pretty serious pretty quickly. In fact, no sooner had we unpacked Spider did we begin to experience problems. One of the carbon fiber tubes that's used in the assembly of the gondola emerged from the box broken in a way that should not have been possible at all because it should take 40,000 pounds to make this come out from here. This motor was also broken and only sort of kind of miraculously in a way that was repairable. And then of course there was the helium tank, which still was not working properly. So I'm going to be honest with you, by the time mid-December rolled around, I was starting to feel pretty discouraged. We were running behind schedule. We were encountering problems that we either thought we had already taken care of or didn't expect at all. And it just seemed like maybe ballooning is a crazy idea after all. You know, maybe we were crazy to think that we could pull this off, no matter how smart and capable our team was. The experiment itself is already ambitious and extremely complex. Then you add on top of that the uncertainties of ballooning, right? The danger of the launch, the danger of the flight. And you throw in on top of that the difficulties associated with our locale, right? The unpredictability of the weather conditions, the harsh conditions, the near logistical impossibility of getting spare parts on short notice. There were just too many variables. And I'm the kind of person who likes to feel like he's in control of the situation. And man, was I in the wrong line of work on some days for that. But we pushed through as a team, and we overcame some of those technical hurdles. So eventually the day came when we had our first launch opportunity. Now you have to treat, even though launches are frequently canceled because of weather, you have to treat every launch opportunity as though it's showtime, right? Because it could be the one. You have to go through all the checklists, you have to test everything, you have to be on your game. In fact, the Spider team that was responsible for rolling Spider out from the high bay onto the launch pad arrived at LDB at 3 o'clock in the morning. And they told me, you know what, you can sleep in for a few hours because we need you to be sharp once it's in the air, right? And we begin testing all the systems. But of course, it's the night before launch, so I can't sleep. I got up at 5 a.m. and I took a 6 a.m. shuttle from McMurdo to LDB. And that would have been fine because we thought we were going to launch mid-morning, like maybe 10 a.m. or 11 a.m. But what happened was at the start of the day, the winds were suitable for launch, and as time went on, they became unsuitable. So Spider was sitting out there on the pad for hours and hours and hours. And 2 p.m. came by, 3 p.m. and 4 p.m. And the NASA ballooning people were starting to say, look, we might have to call it quits. And like I said, this is very typical. But for us, it was kind of problematic because it was already January 1st, and there's a narrow window in which the winds are set up in that circular pattern the way I told you about. No one has apparently successfully launched any time after January 7th. So somebody had to make a judgment call here. Are we going to take the risk of launching in these non-ideal wind conditions? Or are we going to take an even greater risk and wait and hope that we get another launch opportunity sometime within a week? Somebody had to make that call. And ladies and gentlemen, that brings us to 4:59 p.m. on New Year's Day, 2015. That sound is even more ominous in person. So what's going to happen here is the balloon is going to rise up and over the experiment, and then the driver of the launch vehicle is going to drive forward to try and keep Spider directly under the balloon before releasing it. But don't worry, that's supposed to happen. Okay, so he's trying to keep up with it. It's not quite lined up. He just says, whatever, I'll let it go. So that was simultaneously exhilarating and terrifying. I was able to allow myself to feel just a brief glimmer of emotion. Then I had to turn around. I had to sprint back into the high bay. I had to hurl myself in front of my computer workstation. And I had to frantically start poring over screens as the data began streaming in real time. Okay, maybe more like this. And as Spider ascended and we sent commands to turn on the systems one by one, and after a couple of hours, we realized this is going to work. We have an experiment, all systems are go. And I remember that when I sent this command to take the telescopes and move them up like this, and I saw the line moving up on the screen showing that they had responded, one of my colleagues clapped me on the back and he said, "Congratulations." There was applause in the control room, and there was a feeling of elation, of triumph. It's a moment that really stays with you. So during this time, Spider was actually still ascending. And somebody had the forethought to put an ordinary camera pointing downward to give us a spider's eye view of the Earth below. So I have a little bit of footage of that to show you. So this here is actually Ross Island, where we were. And this is just ice here. And I have another one that was taken slightly later when things were a little more stable. So this is time-lapse photography. So everything is sped up to like 30 times normal speed.
Is that still Antarctica?
Yes, yes it is. Okay. So it seems like maybe ballooning is not such a crazy idea after all, right? Sort of. There's still the little issue of recovering the experiment. So we have to actually physically recover Spider in order to get the hard drives back on which the data are stored. And the only problem with that is, well, we observed for 16 days and we were done, right? So that's great because we haven't come all the way around. So why don't we just wait until it comes all the way back around and then recover it? Well, the problem is the flight path looked like this. And it looked like it was going to take it out over ocean. So we didn't want to risk that. So we actually ended the flight and brought Spider down right here, some 2,000 kilometers away from McMurdo Station. So that made recovery, the prospect of recovery, let's say logistically difficult. Actually, pretty much our only hope was that the British Antarctic Survey has a research station here on the other side of the continent, and they have a little field camp here that's supported by an ice runway with these little planes that bring them supplies. So we contacted them and we said, we have to ask you a huge favor. Can you try and fly out to Spider's landing site and recover at least just the data drives? Forget the rest of it, we'll leave that out there for a year and recover it next year. And once again, we were faced with a ticking clock because the last boat out of this station to go to South America was sometime in early to mid-February. And so we landed on the 17th, and they tried to fly out, and they couldn't because of weather, which is just what happens in Antarctica when you try to go anywhere in a small plane. You get delayed because of the weather. So all we could do was sit there and fret, and we were starting to worry that we wouldn't get the data back this year after all that effort. Until finally, on February 4th, that British Antarctic Survey team sent us these pictures. Here's Spider at its landing site. They landed there. They followed our instructions to the letter. And they recovered every piece of equipment from the payload that had data recorded on it. Even the GoPros, which were obviously lowest priority. So that brings our story to a close for today. But of course, in some ways, the story is just beginning. Now that we have the data back and we're beginning to look at it, we have maps of the CMB, we have maps of some of the other things we looked at. We're analyzing the data, so stay tuned.
So we have about 5 to 10 minutes for questions for Jamil. Right here in front.
I just want to know, what's the advantage of the South Pole over the North Pole?
Okay, so the question, turn that on. So the question is, what's the advantage of the South Pole over the North Pole? I think there's two things. So that polar vortex is a little more stable in the South Pole, and you have more like unpopulated landmass that you can fly over. And then the second advantage is political. So you can launch from Sweden, northern Sweden in the summertime, and go westward towards northern Canada. We did that for BLAST, but that's only maybe a 4 or 5 day flight versus 20 days in Antarctica. And then if you try to launch in the winter, you're going over Russia, and Russia does not want any experiment that has a NASA affiliation in their airspace. So that's the political disadvantage of North Pole. Yeah. Yes?
How do you send commands to make the balloon land after 16 days?
How do you send the commands?
Like how did it disengage? It's
Yeah.
attached from the balloon and there's a parachute and that's
Yeah, exactly. So the question is, how do you end the flight? And the answer is that in the cable in line connecting the payload to the balloon, there's a parachute. And what the NASA guys do is they send a radio signal that triggers a mechanism that triggers an explosion that causes this blade to come out and physically sever the flight train above the parachute. So the payload comes down on the parachute, which opens up as it falls. Meanwhile, there's a thread that tears away from the balloon as you cut away from the balloon, and that opens up the balloon and it releases all the helium so that the balloon just floats back down to the ground. So that's called termination. Yeah. Yes?
So is the wreckage still in Antarctica, and you could go down there and unwreck it?
Yeah.
And do experiments again?
Yeah, the wreckage is still in Antarctica. We're going to go there this season, so like November and December of this year, to try and recover the rest of it. And then we have funding for a second flight, so we're going to see what we can salvage versus what we have to rebuild from scratch. Yeah. Hi.
I'm just wondering, was the solar wind a problem? If yes, how was the balloon protected?
Was the solar wind a problem? So what was a problem that is similar are cosmic rays, which are kind of like the solar wind. They're energetic charged particles that come from space. And when you go up there, the rate of arrival of cosmic rays is much higher than down here. So what that can do is it can hit a bit in your RAM of your computer and cause your computer to crash. So there wasn't any danger of physical damage to Spider from that, but there was danger of like a disruption to its electronics, and we had to take that into account. Yeah.
Yeah, you're talking about these gravitational ripples.
Yeah.
Now, don't all objects in the universe emit gravity waves? So how you can discern these specific ripples from this background noise of gravity?
Right. So every object in the universe has mass, and therefore it has gravity. But under normal circumstances, that's kind of a static gravitational field. It's not so much ripples as it is just, a static thing. So the ripples only happen when you have a really dramatic event. Like maybe you have two black holes that are orbiting around each other and they spiral in and they collide, and that can produce gravitational waves. And I think the answer to your question is that both the frequency of those waves and how strong they are is going to be totally different than it is for the primordial gravitational waves from the Big Bang that we're trying to detect. So we can distinguish them on that basis. Yeah.
The frequency of the, it's going to be, the magnitude is going to be greater, and
Yeah.
the frequency is going to be quite different than the static.
Yeah, the frequency is going to be a lot lower, and I think the magnitude is going to be a lot lower too. Yeah. Mm-hmm.
So you have a filter to,
Yes.
you have to tune in to it.
But again, like people who want to look for gravitational waves from objects like that are trying to detect them directly by setting up a thing that actually gets shaken around when the gravitational wave passes over it. But we can't do that for these ripples from the Big Bang because they're too weak. That's why we have to search for them indirectly through the imprint that they leave in the cosmic microwave background. Yeah.
They're too weak for these instruments they're designing, like LIGO and all that.
Yeah, they're too weak for those instruments, yeah. Mm-hmm. Up there.
What's the power consumption of your cable? I just want to know how big your batteries were.
Oh, so it's about maybe 1 kilowatt, and our power system could provide 2 kilowatts. So we had that amount of margin. And then we had just 24 volt lead acid batteries. So we had two 40 amp hour units. Yeah. And that has a lot of weight, but we were able to manage with that. Yes?
Inflation, which I totally don't understand, was it just a theoretically, was
Yeah.
it just a one-time event? Or is it happening here, happening there, this part of the universe, that part of the universe?
Well, I think there are some theories that say maybe in distant parts of the universe that we'll never know about, inflation could be occurring, and only in our pocket did it stop. But the most basic theory is that it was like a one-time event. It occurred, and then for some reason it ended, and it gave way to the more run-of-the-mill ordinary expansion that's happening
Was it
now.
like a second long?
It was like the tiniest fraction of a second long. It was like 0.000, I can't say how many zeros it was, seconds long. And again, the precise duration depends on things that we don't know, that we're trying to find out, like how early did it start, depends on how energetic it was and all that. Yeah. So for our US collaborators, most of their grant funding came from NASA. And in our case, most of it came from the Canadian Space Agency. Yeah. Hi.
So you mentioned about inflation, that's the key rationale. beyond the experiment. So if there was another possibility where it was too differently split out from our expansion, would that affect how the universe would behave down the road?
I didn't catch the part in the middle there. If there was another possibility that,
Well, if the inflation did not happen, then it would happen in the experiment. Or
Yeah.
maybe the data actually shows that the inflation did not happen and something else completely different
Mhm.
filled the gap.
Yeah.
Would that affect like the composition of how like the universe would behave in the further down the road?
it would. And I think there are plausible other scenarios in contrast to inflation that people have come up with to try to explain the starting conditions that we see. But, you know, we're not at the point where we can test the different predictions that those models make versus what inflation makes. Yeah. Hi.
Just a quick follow-up on inflation. Where did the idea come from? Is there any theory on what would cause inflation, or where did the theory even originate from?
Okay, so the question is, what caused inflation? What drove it to happen?
Yeah.
Yeah.
Is there any leads on that?
Yeah, so theorists usually propose the existence of some mystery particle or energy field that drove inflation. And we don't know anything about that because, again, we don't know how early it started and how much energy was involved. So if SPIDER could find out that, then that would put a constraint on what kind of particle or field, you know, was involved. But we know it's not any of the particles that we know about from this particle physics. It's not the Higgs boson or anything like that. Those candidates don't work. Yeah.
Well, we have time for one more question, and please stick around for some announcements about what's going to be going on after.
Okay, up there?
Was your dissertation based on this data that you collected as this, or was it part of something other?
Well, yes, the question is, was my thesis based on the data from SPIDER or from something else? And the answer is, my thesis was kind of a hybrid between the hardware work I did on SPIDER and the analysis of the data from the flights of Blast Pole. So I was involved a little bit with Blast Pole. It was always there as a contingency. And SPIDER took so long that we actually managed to fly Blast Pole twice in the period of time that this story started. So that's what was in my thesis.
Okay. Jamil will be around afterwards to take a few more questions if you wanted to come up and talk to them. Afterwards, or right now actually, we have the telescopes open. It's not very cloudy, so we're going to have